us from Cornell, and he's going to talk about causality constraints and quantum field theory.
All right. First of all, thanks for inviting me. It's great to be back in Texas. So I did my PhD at UT Austin, so nice to be back. So I'm going to talk about causality constraint in quantum field theory and its application in conformal field theories. So this is based on mainly these two papers with Tom Hartman and Sachin Jain, who is a postdoc at Cornell, and also another paper which is hopefully will appear next week. That's with Tom Hartman and a grad student at Cornell, Amit. Okay. So in the life of a quantum field theorist, there are certain things which are sacred. For example, if you are working with a Lorentzian QFT, it's better be unitary, causal, and Lorentzian invariant. Similarly, in the Euclidean space, if you're working in Euclidean QFT, it should be reflection positive, crossing symmetric, and Euclidean invariant. And from the title of the talk, probably you guessed that the talk will be about causality and how that's related to these three conditions in Euclidean QFT. So for obvious reason, causality is a Lorentzian concept. Because just to define it, you need a light cone. And one thing that I'd like to stress in this talk is that causality can impose non-trivial constraints on QFT in Lorentzian signature. And another thing that was important for that is the following. A quantum field theory might appear to be causal in the vacuum state, but it can violate causality in non-trivial states. Because causality is a statement about is an operator statement, so the theory should be causal in any state of the theory. So you are not allowed to violate causality in any state. So if you find some non-trivial state in which causality is violated, that means there is something wrong with the theory.
Why was that? Is this Lorentzian? I didn't hear what you said before.
So it's basically an operator statement, causality. It's basically a statement about if you have two space-like separated operators, their commutator should be 0. So it's an operator statement. So if you can sandwich that in any state, that should be 0. Let me give you an example. This is by Adams, Arkani-Hamed, Dubosky, Nicolis, and Rathaset, 2006 paper. Let's consider a massless scalar with a shift symmetry. You have the standard, it's in any dimension, you have the standard kinetic term, and you have a term which is basically square of this term with some coefficient mu. Obviously, this coupling is not renormalizable because it's just from power counting, you can conclude that. So this is an effective theory. What these guys showed is the following. This theory is causal if and only if mu is greater than or equal to 0. So if mu is negative, there is no way you can find, so basically you cannot find a UV complete theory that will give you this IR effective field theory. So they showed it in two different ways. First was basically a classical argument. So they just took this theory and they found some classical solution of this theory. And then they studied perturbation around that solution. And they showed that there is superluminal modes. So that's one way of looking at it. And the second thing is basically they did a 2-to-2 scattering. And they, from the scattering amplitude, they basically could write down, so they basically used unitarity to write it down in a way so that mu, there is an equation with mu and something which is total cross section. So because from unitarity that the right hand side has to be positive, so basically they had some kind of sum rule. We'll have something like similar to that in safety, but basically they were able to write down mu as some kind of sum rule where the right hand side was positive from unitarity.
Question.
Yes.
Yes.
Yeah, yeah.
Thanks. So was there a result showing that mu was greater than or equal to 0 necessary or necessary and sufficient? Like, could they prove that any mu
It's
greater-
necessary.
Yeah.
I don't think, no, it's just necessary, yeah.
And how do they know about UV completion being fatally
So basically,
non-causal?
so basically what they could do, so they basically use some, basically they were able to write this mu as some integral over the total cross section, and that the right hand side, it doesn't depend, there was no cutoff, so it's basically some, it's on all energies, the integral. But because just from unitarity you know that that thing has to be positive. So if you make mu negative, that means total cross section has to be negative, something like that.
Well, doesn't that sound like a unitarity constraint?
Yeah, that's the unitarity constraint, yes.
But you talked about causality.
So basically, they started with, so in the classical theory, they are considered classical. Basically, they derive this even from the classical theory. So there it was a causality constraint. It was basically superluminal propagation. And we will also derive this from the from causality. So it's actually not, basically from unitarity and causality, you get the same constraint. And actually, we asked Nima about that. He said basically they are kind of related. Like there is some relation, but they don't know what. But obviously, there is some relation.
Now what is the, you said UV completion, but I didn't see that. Why is that necessary for anything?
So it's necessary in the sense, basically, if mu is negative, there is no UV complete theory.
But you didn't say anything about that when you started talking about the axioms of the quantum field theory. You just said causality, unitarity, and Lorentzian invariants. And now we're appealing to possibility of UV completing an effective theory to say something about.
No, not to say something. I guess he's saying if you consider it, it wouldn't help.
Yeah. So basically,
it's up to you to consider it or not. Right?
Yeah,
Right?
yes, yeah. So if you forget about UV completion, this theory itself, if mu is negative, it's safe. And so one might say that okay, it's a IR theory, it can be safe. But they are saying is the following thing: if its mu is negative, there is no way you can, like in the UV theory, you cannot hook up any well-behaved UV theory that will give you this.
You can't cure the sickness.
Yes, exactly.
In this particular example, that's the case.
Yes.
With your initial axioms, you're going to do field theory.
Yes.
There's no theorem that will say that if you run into trouble in field theory, the UV completion will not cure it. In general, you have no theorem, right,
No,
for that.
no.
But in this case, you have a result. They have a
Exactly.
result. Okay.
Exactly. One might also ask the following thing. So there is something wrong when mu is negative, but in the Lorentzian signature, it's causality. So what happens in the Euclidean signature? So even if I go to the Euclidean version of this theory, there has to be something wrong. I will try to address that in this talk. Let me give you one more example. This is from gravity. So let's take 5-dimensional gravity. It's true for any dimension. It's even true for higher dimensions, but let's just consider 5-dimensional gravity with the Einstein-Hilbert term. Then there's this Gauss-Bonnet term, which is basically in R square. So this is the only higher derivative term you can write down in this order, which doesn't have Gauss. M2 is some scale which is much below the Planck scale, and C2 is a coefficient which is of order 1. I also have some negative cosmological constant here. I don't need that, but let me put it here. Their conclusion is true even if you don't have this cosmological constant, but I put it here so that I can talk about RACFT. So in this, if you do perturbative analysis, what you can show is that this this is consistent up to some scale m, which can be parametrically higher than m2. But in this paper by Kamanho, Delstein, Malasena, and Zabiedha, they showed if C2 is non-zero, there is a causality violation. They studied some solution of this theory, then they used graviton in that background, graviton propagation in that background to show that this has to be 0. And there is an equivalent statement about R cube corrections. And let me be more clear about what this means. So in the field theory point of view, so just if you start with this action, you take some solution, let's say ADS, and you do some perturbation around that solution, you can show that just from consistency, you can show that the new physics should appear at scale m. But in the paper, they concluded that new physics should appear at scale m2. Otherwise, there will be a causality violation. Any question? Okay, so what does that mean for in the context of ADS CFT? So let's take some large n CFT which is dual to gravity, which is a gravity dual, and you consider some stress tensor correlation function in that CFT. So basically, from their argument, what you can show is that the endpoint function of stress tensor, it's basically what you get from the Einstein gravity, and the corrections are very, very suppressed. And the suppression, they are suppressed by dimension of new physics operators. So basically, you can actually, you only have Einstein gravity and some very small correction, that's it. And in other words, from their computation, you can show the following. In 4 dimension, the expression value of the trace of the stress tensor, it has 2 central charges. This is y squared, this is cos 1m. Just because you cannot have r square and r cube corrections, from that you can show that for holographic theories, A and C should be equal. However, there is no proof of this from the CFT side yet. And of course, even for large n CFTs, this shouldn't be true for any large n CFT. Because it's not that whenever you have a large n CFT, you have a dual. So for what we guess, if you impose large n, if you start with a large n CFT, and if you impose some assumption like there is the low line spectrum is sparse, probably that should be sufficient to derive this, but there is no proof yet. So the goal of the talk is the following: to understand causality from the QFT side. Causality violation in Lorentzian signature must imply some problem in Euclidean signature, and by considering a CFT, I'll show that causality is encoded in crossing symmetry and reflection positivity of Euclidean correlators. Then I'll show that causality constrains the interactions of low dimension operators of the CFT, regardless of what happens in the Euclid. And finally, I'll provide a proof of the average non-energy condition from causality. So this is the outline of the talk. First, I'll discuss causality in QFT, then I'll constrain CFTs, CFT interactions, then I'll discuss the relation between average non-energy condition and causality, and then I'll conclude. So this is what I mean by causality in a QFT. Take any 2 local operators. If they are space-like separated, their commutator should vanish. And again, let me stress the point that this is an operator statement. So a theory that appears to be causal in vacuum can violate causality. So in the vacuum, this is a trivial statement. But in non-trivial states, this is actually very constraining. So when you compute some correlator in a QFT, you do the following thing. You start with the Euclidean. You start with the Euclidean QFT. You compute some correlator like this, and then you perform some analytic continuation to get the Lorentzian correlation function. So let's start with the Euclidean correlation function. So this is a single value permutation invariant function of positions. By permutation invariant, I mean in this correlation function, if you choose the ordering of 2 operators, this value shouldn't change. And that's basically the permutation invariant is basically the crossing symmetry of the Euclidean correlator. let me choose some direction tau randomly, and I'll perform an analytic continuation of this direction to get the Lorentzian correlator. So this G.
What's the fiscal principle behind permutation invariance?
It's not. It's basically in the Euclidean signature, operators do commute. So as long as they are as long as they are separated, they will commute because basically there is no light point. So because of this is basically that. So if you change the ordering, it shouldn't matter.
But in a term.
But it was the same operator, right? To every insertion.
Yes, yeah. So ordering doesn't matter in Euclidean language.
And you really mean permutation, not just cyclic permutation.
No,
permutation.
permutation. So basically, just take any correlator, just in any ordering, you'll get the same thing. This G has some nice properties. For example, G is analytic from coincident points, and this function G doesn't have any branch cuts as long as all the points remain Euclidean. And this is because it doesn't have any branch cuts, or it's basically because it's analytic, which is basically a consequence of the fact that in Euclidean signature, operators do commute. Now there is something called Reconstruction theorem, which guarantees the following. If you start with well-behaved Euclidean correlators, upon analytic continuation, you get well-behaved Lorentzian correlators. And by well-behaved, I mean the Euclidean correlator is analytic away from the coincident points, SOT invariant, permutation invariant, reflection positive, which I'll discuss later, and obey certain growth conditions, which is not important for us in this talk. And by well-behaved Lorentzian correlator, I mean it's unitary, causal, and Lorentzian invariant. And by unitary, I mean any in the Lorentzian. If you can write down some Lorentzian correlator as norm of some state, that has to be positive.
Does the reverse hold?
Yes. So there is one-to-one correspondence. Yes.
Who proved that? Same people? Or?
Yes. And in CFT, there is something. There are even stronger. The statements are even stronger. It's called Lasher-Mark construction, probably. So, but yeah, this is basically very general. There is, as far as I know, there is yes, there is one-to-one correspondence. Yes, exactly. But one thing that's not there, that's basically, if it's not like if let's say you just have unitary Lorentzian invariant, you don't have causal, you don't know what will go wrong in the Euclidean theory.
Similar statements are not known for ADS invariant theories. Right? This Poincare invariant theory you're talking about.
This is
the Lorentzian sector.
Yes, I don't know of any such statement.
Okay.
Now let's go to the Minkowski space. Okay, I'll start with the Euclidean correlator, and I'll perform the standard analytic continuation, tau to IT. So as a function of complex tau, Euclidean correlator has an intricate structure of singularities and branch curves. So because of that, this analytic continuation is ambiguous, because whenever there is branch curves, you can actually choose which way you can perform this analytic continuation, and that leads to ambiguities. And that's actually not bad, because each choice that we make in analytic continuation translates into a choice of operator ordering in Lorentzian signature. So there is a one-to-one correspondence. If there are 4 ways you can perform some analytic continuation, then in the Lorentzian side you have 4 different correlators, depending on the ordering. And because of that, in Lorentzian signature, it matters. The ordering matters, and because of that, there can be non-vanishing commutators. Let me give you an example. Let's consider this 4-point function: O1, O2, O3, and O4. O1, O3, and O4, they are at t equals to 0, but I'll take the operator O2 and I'll move it up and down to see what happens. When O2 is here, it's basically space-like separated from other operators. So now, when the configuration is this, then the ordering doesn't matter because everything is space-like separated. Now, if I compute this correlation function G as a function of tau 2, which is the Euclidean time of the operator 2, it has this branch cut structure. First, there is a singularity here. This is when, if I move O2 upward, when it hits this light cone, that will give you the singularity and this branch cut. Similarly, if you move it in the upward direction, it will hit the light cone of O3. That gives you this singularity and this branch cut. Now, let me discuss how to, when you have branch cuts, how to do this analytic continuation. So what are the rules? First, as I said, start with some tau 2 equals to T2, and then go to the imaginary axis, somewhere at I T2. Each time we pass a singularity, we must choose whether to pass to the right or to the left. Passing to the right of a singularity puts the operators into time ordering in the resulting Lorentzian correlator with respect to the operator responsible for the singularity. Passing to the left puts the operator in anti-time ordering. For example, when the operator O2 is somewhere here, that's basically when it's time-like separated with respect to O1 and O3, but space-like separated from O4. In that case, you can show that there are 4 ways you can perform this analytic continuation: right, right, left, right, right, left, and left, left. And that corresponds to 4 different ordering in the Lorentzian that you can actually write down in the Lorentzian signature. Let's take this P. So it's right of the singularity because of O1 and left of singularity because of O3. So because of that, you have O3, O2, and O1. And obviously, this will give you the time ordered one, and this will give you the anti-time ordered one, as you can see here. Now let me talk about causality. Let's take a simpler example where you have psi, O, psi. I'll start with a configuration where all of them are space-like separated. Then I'll move operator O2 close to the right cone of the other operator O. This is generally known as the light cone limit, and at least in CFT, in this limit you can actually perform some computation. Now, if you start with the Lorentz Euclidean correlator and you want to compute this Euclidean correlator from that, again, let's draw the branch cut structure of the correlator, and also let me note that when we do the analytic continuation, whenever you encounter some singularity in the Euclidean correlator, that's when you get some non-vanishing commutator in the Lorentzian picture. The reason is the following. So let's say you start from here, you perform this analytic continuation. If you pass this singularity, then and only then you have a choice of going from the left or from the right. That gives you different ordering. So let's start from here, and because we are moving towards the light cone of O, so basically we are approaching this second singularity. This is basically the operator O psi psi. So if we do not cross any branch cut, then the singularity of the Euclidean correlator are determined by the light cones, because that's where they should be. However, if we perform this analytic continuation, because we are crossing this branch curve, it's not obvious that the this singularity will stay here even after we cross this branch curve. So that this is basically this ordering psi OO psi. And for this operator, the commutator OO in this state will be non-vanishing when we hit the singularity, when we hit the next singularity on the second sheet, not on the first sheet. And as I said, it is not at all obvious that the second sheet singularity is at the O light cone. So the bottom line is, on the first sheet, causality is trivial, but on the second sheet, causality is actually very non-trivial, and this is the case which will give you non-trivial constraints. Let me make a few more comments. Again, if we do this analytic continuation, and after crossing the branch curve, if we find that this singularity moves in the upward direction, that means basically the OO commutator becomes non-zero at a later time, which is alright, because that means there is some kind of time delay. However, if after crossing the crossing this branch curve, if this singularity moves in the downward direction, that means the commutator becomes non-zero when it shouldn't be. It becomes non-zero at an earlier time, which is equivalent to some time advance, and that means basically the theory will become acausal. So on the second sheet, this singularity is not allowed to move in the downward direction, and that's when you get, and imposing that will give you constraints. Any question? Okay, so summary. Starting from a Euclidean correlator, causality on the first sheet is obvious. The non-trivial statement about causality is a constraint on how singularities in the complex tau plane move around as we pass through other light cone branch curves. Causality violation in Lorentzian signature must imply some problem in Euclidean signature, and I'll show that causality of the Lorentzian correlator is encoded in reflection positivity and crossing symmetry of Euclidean correlator.
This would be a technical question.
Yes.
If you go back, when you do these calculations, is the starting point a known endpoint function? I mean, most of your work is not trying to obtain correlation functions, but given correlations,
Exactly.
you want to study how they behave.
Yes.
As you do the continuation.
Yes.
Is that the point?
Yes, exactly.
Okay.
So far, whatever I said is true for any QFT, but we don't have position-space correlation function for any QFT. So,
but the endpoint functions are rather model dependent, though, aren't they? Because this is not CFT, after all. It's FT.
yes.
Field theory amplitudes are, how can you treat them so generally, I wonder, without having a model to talk about?
So, because like we already know the behavior of the Euclidean correlation function, that's universal. Like, take for example the singularity structure, branch curves, those are universal. But
So you don't need actual answer in terms of polarizations, etc.,
Yeah.
which are model-dependent details, like
Yes.
coupling constants.
yes,
You don't need all that.
I don't need all that.
Formally, you take the endpoint function, formally written,
Yes.
and you know it's in Euclidean space, let's
Yes.
say, and
Yeah.
then you try to continue it.
Yes. So if you give me a model, then I can basically, if you give me a correlation function, I can use this technique. Then basically that will give you constraint on the couplings and things like that. So if you want to use it, then you have to know the theory.
Okay.
I didn't understand the physical intuition for why you need more than one of the ways of passing. So in the picture,
Mhm.
you have a boundary condition, which is that whichever O you're moving came from the causal past of all of the other operators. And so then there should only be one way that you pass around, the singularity. But is the idea that, well, that was only one configuration and we could have started with a different configuration? And so every way of passing through light cones has to be compatible?
Yes. So basically, when you initially you are starting with operators where they are space-like separated. Everything is space-like separated.
Yeah.
So that's you can compute that from the Euclidean correlator. But the thing is that the point is you can actually compute the correlation function even when they are time-like separated, and they come from the same Euclidean correlator, because in the Euclidean signature there is nothing else. So basically the fact that in other words, all the possible Lorentzian correlators, they are basically analytic continuation of each other. So that's the idea, and they are related to the correlator when they are space-like separated. So that's why basically if there is one way of doing this analytic continuation, that means basically even in the Lorentzian signature there is no, the operator ordering shouldn't matter. But that's not true. That we already know. Any other question? Okay. So now let me put constraints on CFT interactions. To do that, we'll start with a shockwave state. Let me define a shockwave state. There is some operator psi which is inserted in the Euclidean direction at Euclidean time equals to delta and in the origin of the Lorentzian space. And this thing operates on the background state, and this is the state in the limit delta going to 0. This is the state that I'll talk about in the rest of the talk. This is known as shockwave state for the following reason. If you take this state, if you compute the stress tensor expression value, you can show that it has support on an expanding null shell. So it behaves kind of like a shockwave. And we'll consider this 4-point function, psi, O, psi, where psi is the thing that creates the shockwave, 1 O is here, and so this O is space-like separated from both of them, but this O is time-like separated from both sides. And this operator approaches the light cone of the other one. Now if you compute the commutator of O in this state psi, that must vanish because this O, they are space-like separated. So causality requires that singularity as OX3 approaches the OX light cone cannot appear too soon. That means when I push this operator towards this light cone, there shouldn't be any singularity on the left-hand side of this light cone. The singularity can be here or it can be on the right of it. But there cannot be anything on the left of this light cone. You can do some algebra to show that this this is equivalent to this statement. G should be analytic in this red region, but this red region is some complexified region of spacetime just before the light cone. And you can show that these two are equivalent. So there the correlator G should be analytic in this small region. Now, before I tell you why a well-behaved Euclidean correlator should be analytic in this region, let me give you some comments on crossing symmetry. As I said earlier, crossing symmetry is the statement about permutation invariance of Euclidean correlator. You are allowed to change the ordering in Euclidean signature. So this is actually a very old idea by Polyakov, and it's from a 1980 paper probably. But after that, people forgot about this thing, and very recently in 2008, Ratazi, Richkov, Tony, and Vichy, they showed that this can be actually very constraining, and they actually use crossing symmetry to exclude theories. Just this simple fact can be used for example, for let's say 3-dimensional Ising model, to study 3-dimensional Ising model with very high precision. And this is known, goes by the name numerical bootstrap. Also very recently, not actually very recently, 2012, people used crossing symmetry for Lorentzian but space-like separated correlator. And again, this is mainly a work by Mark Gorski and Zavieda. They showed if you crossing symmetry will actually tell you a lot about the spectrum of a CFT. It can tell you about universal behavior of some anomalous dimension of double trace operators and things like that for any CFT. However, our problem is a little bit more difficult because we need crossing symmetry for time-like separated operators. The second thing is reflection positivity. It's the following statement. If you have any number of operators in Euclidean signature, O1, O2, and you can have more, and you have the same bunch of operators, but one of the direction, in one of the direction you have minus of itself. This thing is greater than 0. Basically, you can write this as norm of some state, and because of that, this has to be positive. And using these two statements, you can actually show that the correlator G is analytic in this region. Let me explain why. Generally, when this operator approaches the light cone, you can perform some OP expansion in this channel, and that's something you can actually compute. But though you can compute in this channel, that's not very, that will not tell you the analytic structure of the correlator. But crossing symmetry allows us to expand in the channel O psi, so we can expand in this channel. Though it's an infinite series, you can actually show that by expanding in this channel that this correlator is analytic. And because of crossing symmetry, we know that it doesn't matter which channel we expand, we should get the same result. So that means the correlator is analytic in this region. So basically, that means the correlator is causal. So reflection positivity plus crossing symmetry of the Euclidean correlator gives you causality, and now I'll use that to constrain IR coupling. Now, just as I said, correlator is analytic in this region. Now let's zoom this region like this, and because the correlator is analytic, if you perform some contour integral of G minus 1, that has to be 0. This looks like a very simple expression, but actually it's very important for us because in this regime you can actually compute the correlator. It goes by the name light cone limit. In this limit region, if you compute the correlator, it's basically, it has this form: 1 minus some numerical factor times this. So basically, it's dominated by some operator. So if you have a theory where you have find out the lowest twist operator. Twist is dimension minus spin. Find out the lowest twist operator. That will give you the dominant contribution in this region. But the problem is you don't know how to compute this correlator close to the origin, because in this region all the operators will contribute. But because of analyticity, you can perform this contour integral, and you can write down this lambda m equals to some line integral like this. But from reflection positivity, you can actually show that this thing is it has to be positive. So that gives you lambda m greater than or equals to 0.
You mentioned lowest twist operator.
Yes.
Right? Yeah. If you are in 4 dimension, would that be a renormalizable operator or?
Generally, it's always
not?
the stress tensor.
Stress tensor.
Yes.
Okay.
So basically, what you can do, you can write down lambda as some line integral which is positive. So this is the important thing. When you compute this 4-point function where O can have any spin you want, psi is scalar, and it's normalized by the 2-point function. It should always go like this: 1 minus something positive times something which depends on the position. So if you compute this correlator for any this correlator for any operator O and psi, whatever you get here has to be positive.
What is delta?
Delta is basically the thing that created the shock wave. It's basically
It's a
some
positive
energy.
number.
Yeah. It's basically the energy of the state.
Real positive number. Okay.
Yes. So just compute this. Whatever will appear here, that has to be positive. For simplicity, let's take O to be scalar. Then it's very easy to perform these computations. And again, let's consider a very general case where your theory have multiple operators with the same minimal twist, but with different spin L. Now, if you use this fact, you can show the following thing. There is no constraint on the spin on lowest twist operator. Second thing, there is no constraint on the spin 1 conserved current. There is no sign, yeah. The second thing you can show is the following. If you have the spin 2 conserved current, which is basically the stress tensor, the OP coefficient OOT times psi psi t, that has to be positive. And this is somewhat trivial because from one identity you can actually compute this quantity and it's positive. But the more important constraint comes for the higher spin conserved currents. So any finite number of them is excluded. And that was actually initially shown by Madasena and Zaveda for in 3 dimension and in 4 dimension by these other people. But for us, it actually just comes from our construction. Therefore, a theory with even one higher spin conserved current must have an infinite number of such currents with fixed coefficients.
Does that mean that the derivative of scalar raised to some power higher than 2 will be non-causal? The result you are citing at the beginning of your talk. Can you make a connection with that statement? You mentioned the result where you had mu, d mu phi to what power was it again?
Del phi fourth.
Fourth, yes. Is that ruled out by this?
Not really, because like it was almost free theory. So for free theory, because there are infinite conserved currents. So there are many ways to look at that. So one way would be just put that thing in ADS. So then for the boundary safety, you can actually show that you will violate the last condition. So that's one way you can do it.
I'm trying to see how the statement of higher spin conserved current translates into information about the Lagrangian field theory. What couplings can I exclude? That's what I'm trying to understand. If I want to use your statement, Ln greater than 2 is excluded, what do I learn about the interacting field theories? What kind of interactions am I ruling out? That's it.
I don't know of a direct connection.
Well, then,
You know, one thing that would work.
sorry?
You know, one thing that would work, which is that there's higher dimension operators have the system should be integrable, and then you'll have an infinite number of such currents, and maybe something can happen. But I think it's just saying if you have some one, then you have to have. So the other one, the reason you can avoid it maybe with the partial phi to the fourth, is that thing will have an infinite number, could possibly have an infinite number of conserved currents, so it can avoid this problem.
I don't see how the conserved current business enter the discussion of the field theory itself. If I give you a scalar field theory, which is your example, isn't it? And there is no higher spin fields, for example, right?
But there is stress tensor, there is a stress tensor, which is conserved in spin and spin 2.
Yeah, but it's a field theory. It's just scalar field theory. I think you're talking cross purpose. It's not a higher spin gauge theory. There are no higher spin. There's no graviton even. You're building an operator out of scalar field. Operators you can build.
Yes.
I agree.
Yeah.
So therefore, our main theory is the scalar field theory. Is it not?
It's scalar field theory, but we already know that you can build at least one operator, which is the stress tensor, which is conserved and spin 2. So del phi to the power fourth, it's not, so because in your theory you already have a minimal twist operator, at least del phi to the power fourth should have that twist, but that's not the case.
Yeah, but why are we talking about twist operators if we cannot convert that into information about the
So
effective field theory. I mean, yeah, plot in
So this is
traction.
so far a CFT statement.
Yeah.
So yes, I don't know of a similar statement for a field theory. Yeah, that I agree.
Mhm.
So the problem is basically again like I don't know how to compute the 4-point function.
Okay. That
And-
helps at least now. Okay.
And but one thing that we have been working on, but with very little success, is just to translate everything in momentum space language. Then we can say a lot, like, but we don't have it yet.
When you say high spin, you mean what? Spin equal what?
High spin,
Yeah.
anything greater than or equal to, greater than 2.
Greater than, should be greater than. And what about if you had multiple spin 2s?
All of them conserved or not?
Well, if you had 2 spin 2s that are conserved, twist 2s, I guess.
So if you have two spin 2 and let me see. So there will be a constraint like this plus that, like there will be a constraint on the whole thing, sum of the.
Oh, I'm sorry, I didn't read the first one. It has to be different.
If
So you twist different spins.
yeah, but let's say if you have two spin 2 with the same twist, then you have a constraint C O T1, C psi T1 plus C the other one, sum should be greater than 0. Yes.
Is this element greater than 2 excluded supposed to follow from the previous?
Yes. One easy way to see is the following that. There are many ways you can see that. Basically, we can actually show that this is how the 4-point function should behave with this delta and everything. Now, if you go back here, this is actually for any spin what you get. So you can see that I need delta 1 over delta. So if you have any high spin operator, but you have, they will be the leading one because delta is very small. So because you need 1 over delta, so because of that, everything else is excluded. What can happen is that basically you can have an infinite number of them, and after summing, it becomes subleading. Just for a sanity check, we actually derived this mu greater than or equal to 0 from our by our method, just by computing the 4-point function and showing that just from the analytic structure of the Euclidean 4-point function, you can actually show that mu has to be greater than or equal to 0. So I forgot to mention one thing about this theory. This is just not a cute observation. This played a very big role in the proof of the theorem for RG flow in 4 dimensions by Komarkovsky and Schumann. Now let's consider spinning external operators. Just from conformal invariance, you can show that JJT, but T is a stress tensor, J is spin 1 conserved current. It has the following structure. Basically, this is the tensor structure that you get for free scalars. This is the tensor structure you get for free fermions. And NS and NF, there are some coefficients. So this is the so basically JJT has 2 tensor structures. Similarly, you can show that TTP 3-point function, it has these 3 structures with NS, NF, and NP. So from our method, you can actually show that all of them should be positive. And this is actually a very interesting result. Let me explain why. So we derived this from causality. Basically, we derived a subset of this constraint initially. Then a month later, Hoffman, Lee, Melzer, Poland, and Visan-Barrera, these are bootstrap experts. They derived this whole set of constraints. Then you can also show that from deep inelastic scattering, you can derive the same kind of constraint. That Komarkovsky, Kulaksidze, Parnachev, and Sovietov, they derived this by demanding unitarity for some deep inelastic scattering. Basically, this for both these conditions, you should start with some 4-point function, and you do some algebra to get this condition. But the interesting thing is, Hoffman and Madasena derived this back in 2008 by demanding that the CFT obeys average null energy condition. So they basically argued that this is something, this is a reasonable thing to assume for CFT, and by starting from here, they derived all of them. That's very interesting because a priori there is no reason why these two should be the same. For this, we start with the 4-point function, you get this. For them, they started with some 3-point function, they assumed average null energy condition, and you get the same constraint. In fact, you can actually show that their condition is way stronger. For when you have non-conserved operators, constraint you get from here is stronger than constraint that you get from here. The reason, there is one reason, because for causality mainly, you have to start with some state, and you can start with any state you want. So somebody can be very clever and come up with a state where you get the best kind of constraint. But for them, the state was kind of obvious. So probably we thought that probably we are not choosing a state correctly. There should be some other state in which we can do better. So that leads
the method. This method seems to be the easiest, the most
the last one?
null energy.
Yes.
Compared to all the suffering you have to go through with causality.
Yeah, so from
and
here
yet it gives the strongest condition. Isn't that remarkable?
And the reason is basically, that's the next part of my talk, you can derive this from causality. So basically we have a proof of average null energy condition from causality. And the proof, then before that, this is statement of average null energy condition. U is the light cone coordinate. So basically integrate over the light cone coordinate, take the expression value, that has to be positive or non-negative. Matter violating NA, which is a short form of average null energy condition, if it existed, could be used to build time machines and violate the second law of thermodynamics. This is very important in gravity, and in gravity there are many other energy conditions like dominant, strong, weak, null, etc. But unlike them, so far, NA has no known counterexamples. So this might be something which is actually true in a QFT.
What do you mean by true and good?
So basically, you can actually show that all of them, even for simple QFTs, they are violated.
So okay, the integral is taken over any geodesic in flat space or something.
Null geodesic, any null geodesic,
No.
yes, yeah. NA is a non-trivial statement about QFT even in flat space without gravity. As I said, it gives you these conditions. In another way of saying it, it gives you this bound on A over C. If A over C is outside this bound, basically average null energy condition will be violated. The first general argument for NA in QFT was found just very recently by Faulkner, Ley, Pariker, and Wang from positivity of relative entropy. However, there is one subtlety. Relative entropy is something similar to entanglement entropy, and this positivity argument, this was derived from quantum information theory. So basically, they have some discrete system, and they derive this positivity of relative entropy. But as like any other quantum information theoretic argument, it is not very clear if you take the continuous limit if that's true or not. And in fact, it is almost it's impossible to derive this for a QFT. For discrete systems, you can actually derive it, but for QFT, you have to assume that it's true. So we asked if there is a more general connection between causality and NA in QFT. For that, we start with this 4-point function, psi, which are almost like separated, and operator O. O can be anything. It can even be a non-local operator. It can have any spin you want. So it's an arbitrary operator. The key observation that leads us to the NX is the following. The operator product expansion of psi, you can write it down in this way. 1 minus something positive times this integral. And as you can see, this is the exact thing that appears in NA. Now the rest is somewhat simple. Causality tells you this 4-point function should go like this. 1 minus I times something positive times some function of E and U. Now using the OPE, you can actually compute the left hand side. It turns out to be this. So the thing that has to be positive, that becomes this. Now as I said, this is true for any operator O. Local, non-local with any string. So that means this has to be positive.
I'm sorry, I have a problem with this. You have a coefficient multiplying this.
Yes, that's positive.
What if the coefficient is negative? Then this could be negative too.
Yes, so basically you can
product which has to be positive.
Yeah, so this is positive.
No, but that was a condition you want to impose.
No, this is you can derive this.
Oh, you derive it in this case.
Yeah. So basically, this is a statement about operator product expansion.
I see. Okay.
This is the key thing. So basically,
okay.
These are the leading order terms as v goes to 0.
This is the leading order term as v goes to 0. Yeah, precisely. So yeah, this is to be more precise. If v goes to 0, then you take this to go to infinity. And this. So this is a result that hopefully will appear this week or next week. So some comment. Our argument is essentially a UP argument. And all of it depends on the fact that we were able to use that operator product expansion. So therefore the conclusion should hold even in non-conformal KFTs as long as there is an interacting UP fixed point. See, as long as I can use that OPE, I can prove this. So that means basically an average energy condition is true even for non-conformal KFTs as long as you have interacting UP fixed point. And more importantly, it is very easy to generalize what we did. And we could actually show that NA is just one example of an infinite class of positivity constraint in CFT of this form. Let me explain what's this. So just take any event spin S, find out the lowest dimensional operator that you have in your theory that will obey a similar constraint. And we actually check. This is the strongest constraint that you can get for any CFT. We take different types of 3-point functions. We derive constraints using all the known methods. This gives you the strongest one. So what we are working recently, so we want to use our positivity condition to constrain all 3-point couplings in a CFT. Then another thing that we are interested in is to derive A equals to C for large N CFTs with some appropriate assumptions. We don't know what assumption we should take right now, but this is something we would like to derive. And finally, derive constraints for other relativistic quantum field theories without conformal symmetry. This is the most difficult one so far.
Aren't the 3 points determined by symmetry in CFT?
Yes.
So why is that an open problem?
Which one? This one?
Yes.
So basically, but we didn't have this before. We didn't have we didn't know that 3-point function should have any condition.
So what you are saying is that although any CFT has well-defined 3-point functions by symmetry,
yes,
still we have to subject it to a constraint.
Yes. For example, like as I said here, something like this. So CFT tells you that it should have this structure. That's it. But so probably this could be anything.
Oh, I see. Those are not fixed.
Yes.
Okay.
So let me conclude. Causality places non-trivial constraint on KFT in Lorentzian signature. In CFT, causality is encoded in crossing symmetry and reflection positivity of Euclidean correlators. Any finite number of higher spin currents in CFT leads to violation of causality. Any unitary Lorentz invariant QFT with an interacting fixed point in the UV must obey the average non-energy condition, otherwise microcausality is violated. The average, when I say average non-energy condition, I mean the whole infinite set. And its higher spin generation imposes no strong constraint on 3-point couplings in CFT. Thank you.